So right triangle has two short sides of, let's say, 12 and 11. And then we're supposed to find the other side and the other triangle. So I'm going to rephrase it. I have my notes from a couple of years ago in front of me, but I'm just going to rephrase it and say, solve the triangle. And that means find all the other features that you're not given. So I want to ask what you think about this. Since it's, at least for now, just you and me talking. I don't want to assume that I don't assume that you do know something that you don't, and I don't want to assume that you don't know something that you do. So just from that description, can you tell me, without really doing a calculation, it's kind of implied, can you tell me about any of the angles involved?
What do you mean by angles? Like if it's isosceles or?
Well, isosceles refers to the triangle being isosceles, but an angle could be an acute angle or an obtuse angle. Like less than 90 degrees would be acute, more than
Right.
90 degrees would be obtuse. Does
Well, I mean, it'll be a right angle because it says,
Yeah. So what can you tell me what degree measurement that would be?
oh, 90 and
Yeah, 90. So right triangle, that means one of the angles is 90 degrees, right?
right.
Cool. Okay. So I'm just going to make up a picture. I'm not going to worry about it being accurate. I'm just going to draw kind of a right triangle, and then I'll label the two short sides because the problem says two short sides of 12 and 11. So I'll just call 112 and 111. And I'm not going to worry about the drawing being accurate because maybe it's not. I'm not going to,
Okay.
I'm not going to, how can I draw it accurately before I know the numbers, right?
You're fine. Yeah.
Sure. So now what I can do is I need to find the hypotenuse, how long that is,
Mm-hmm.
and I need to find the two other angles inside. And the order I do that in doesn't really matter. That's up to me. So I'm gonna go ahead and find the long side first because that's just Pythagorean theorem. If I call this side C, right, like ABC, then A squared plus B squared equals C squared. And I can plug the 12 and 11 in. So this is 12 squared plus 11 squared equals C squared.
What is that called?
So yeah, I'm sorry.
What is that called again?
Pythagorean theorem.
Pythagorean theorem. Oh yeah, I totally forgot the name.
Sure. Yeah, the name isn't necessarily the most important thing. Knowing what to do with it is more important. But if you
Mm-hmm.
want to tell someone, oh, just use the blank, well, of course it'd be nice to just have the word. Okay. So 144 plus 121 equals C squared. So 265. So C equals the square root of 265. And sometimes we want a decimal number. So let's go ahead and do that with this one. Square root 265. Okay. So I get 16.279. So a little bit more than 16. So that's that hypotenuse done. We got that. So now I can get either one of these angles. It doesn't matter which one I get first. I'll pick that one because it doesn't matter. Just gotta pick one. So I need to label this something, and I could pick any letter. I could call it X if I wanted to, but it's more standard. You're gonna probably see in my math lab, and if you go on YouTube to find videos for this, it's pretty standard to use capital letters like A, B, C.
Mm-hmm.
I'm gonna use Greek letters because that's what we've been doing for angles. I'm gonna call this alpha, and I'm gonna call this other one beta. Okay. So if I want to find alpha, I can use really I can use any one of the trig functions. I could use sine, cosine, or tangent. It doesn't really matter. Um, so uh, well, I have three options. It ultimately does not matter which one I pick. However, if I use sine or cosine, like if I say sine alpha equals whatever number, then I would have to use the C in order to do that. right? And it's a number I've calculated, and typically I think that it's better to avoid reusing numbers you've calculated if you can, because it keeps, well, there's really two reasons. The numbers stay simpler if I use 11 and 12 versus the square root of 265, that 11 and 12 are just easier numbers. But also, if I were to use this rounded decimal approximation and I use it to recalculate another thing, when you use a rounded number in another calculation, you increase the amount of error you're going to have at the end. So for this course, it's not super important to have as much precision as possible all the time, but you're in my math lab, your answer might not be accepted if you used a rounded number and then the thing that you got as a result at the end is off by too much. And then Jack, what major are you working on? What degree plan?
Biology.
Biology. Okay, so depending on what you do in biology, there's either quite a bit of math or basically none. There's some statistics.
I
Yeah.
have to take calculus for biosciences.
Right. Yep. Well, depending on what you go into, ultimately, I don't know, what your goal with the degree is, but if you study behavioral biology, there's differential equations in that. It's fairly complicated. If you go into, if you go into medicine or something, well, yeah, there's some arithmetic and algebra. There's some statistics involved, percentages,
Right, like I want to be like a radiologist, so I have to like
Okay.
know the images and like do like angles and
Okay. All right. So probably not calculus really, but definitely like you're saying angles and measurement and things like that. Okay. Cool. So that means you're probably not going to have to. I mean, you might have to take a class in behavioral biology, but you're not going to use that every day for the next 30 years. So I guess we shouldn't worry too much about the more technical aspects of this. Anyway, I'm going off on a tangent. So what I'm going to do is I'm going to say I'm going to use, since I'm doing alpha, I'm going to use the opposite and the adjacent, right? The essentially y over x, essentially, right? So this is going to be 12 over 11 will be the tangent of alpha. So I can say tangent alpha, tan alpha equals 12 over 11. So that means that alpha equals tangent inverse of 12 over 11. For right triangles, we can always solve this way. We don't have to worry about the period. Oh, is this all the solutions? For section 4.1, we're dealing with right triangles. The inverse trig function plugged in with the calculator will always give you the right result. You don't have to worry about, oh, do I have to add pi to this? It's not going to be a problem. Because if you think about it, this angle alpha, it's an acute angle, right? It's one of the other angles in a right triangle. It can't be more than 90 degrees because the right angle, that corner, is already 90 degrees. How could another one be more than 90 or even equal to 90? There's no room in a triangle for that. So we don't have to worry about that in a right triangle. Anyway, again, I might want a decimal approximation. And also, when I'm using my calculator to do this, I need to make sure that I'm in degrees mode, and I am. So tangent inverse of 12 over 11. So I get 47.90. 47.490, and this is in degrees. Okay. If I wanted, so there's alpha. We have a number for alpha, and again, I'll point out that this is the exact value of the angle, but it's not very tangible. So we'll typically use this because it's more recognizable as an angle or quantity. Let me ask you something. Based on how we just, well, there's two ways to do this. So perhaps based on how we just found alpha, can you tell me how we could find beta?
11 over 12.
Yeah, exactly. We could do tangent beta equals 11 over 12. That would totally work. Do you see how maybe there's a quicker way to do this? Like okay, I'm sorry, I'm not trying to interrupt you, but like instead of doing this, do you see a different way?
No, sir.
Okay, cool. So
Or could you do like, is it something involved with a 90-degree?
Yeah, it is. So, how many degrees are in a triangle total?
3,
3? Well, okay. There's 3 angles, but how many degrees would that be?
180.
Yeah, 180. So that means that alpha, let me do it down here, alpha plus beta plus the 90-degree right angle have to total up to 180, right?
Mm-hmm.
But I know what alpha is. I just found a number for it. So I can do this. I can subtract 90 on both sides. So I'll get 90 degrees and then subtract alpha on both sides. So beta equals 90 degrees minus alpha, right? And that's approximately 90 degrees minus. Now this is quite a bit of writing, but I don't have to use trig functions. So conceptually, this is a lot less work, although it is quite a bit of writing. Because I'm showing all the steps rather than just saying concept and moving from there. So that's going to be 42.510 degrees. So again, as I said, this was not a lot of writing, but conceptually it's way more complicated because I have to use a trig function.
Mm-hmm.
This is just using the fact that the angles add up to 180. So,
So
you
like
know,
when you have the 90 and then you find uh when you find the other angle, you just add those together and then subtract from 180.
yeah. Now, this is not the quickest way to write things. So I could even be a little more clever than that. I could do the following. I could look at this triangle and say, well, I know that alpha plus beta has to be 90 degrees because, without writing all the arithmetic out, I know the total degree measurement for the whole triangle will be 180. And I know that 90 of it is already taken up here. So I know alpha plus beta is 90. So to, to, to do this in short form, I can say, oh, well, beta equals 90 degrees minus alpha. And that's basically, that's cutting out having to write this part. I can skip writing that out if I just
Mm-hmm.
cut to the chase with this guy. So I can save you a little bit of writing. And then it's both conceptually simpler than using tangent, and it's not really much more writing. Anyway, so that's basically that example. In fact, I'll get rid of this. I don't really need that anymore. We were given a triangle. We found out, hey, here's the hypotenuse. Then we found out here's this angle alpha, and then we found out here's this angle beta. So that's all the components of the triangle. So we can say that we've solved the triangle. Does that process kind of make sense?
Yes, sir.
All right. Do you have any questions?
So far no.
Okay, so how about this? I'm going to do an application problem that basically we kind of have to use the same components here. We have to use maybe tangent. We have to use maybe the fact that the 3 angles add up to 180. And I'm going to solve an application problem. It's one that I put that PDF on Blackboard with the lecture notes from a previous, I guess, 2 years ago. And not just here are the examples I did, like the statements of the examples, but here's, they're worked out completely. So I'm going to do one of those. But I need to, I'm sorry, give me a second, zoom in. Okay. So let's say that some sort of aircraft is taking off from an airport. Okay, so let's say a plane, let's call it that. A plane takes off from an airport, let's say bearing north 35 degrees east. North 35 degrees east. And let's say, and travels, let's say 600 miles per hour for 75 minutes. Let's say for 80 minutes. Okay. So let's assume that there was some sort of error in the flight path. They have to do a correction. Oh, we need to turn because we're off course, right? And let's say they're off by a lot. It's like a big mistake. So let's say there's a course correction. So the plane turns. Let's say 90 degrees, because that makes sure that we have a right triangle. That makes the whole problem a little bit more doable. So it turns 90 degrees. Let's say left. Yeah, let's say left. Um, after let's say after 40 minutes, after 40 minutes, at what heading is the plane from the original airport? Um, Maybe it's some, what I like to try to do in courses like pre-cal and cal 1 is to have examples that are in a bunch of different um, disciplines. So I'm going to have to work on adding something. Basically, tree functions show up a lot in engineering and physics and chemistry. And biology, basically, I think they're most common in, okay, so for example, talking about, you know, radio waves, that's present. And I would assume things like, you know how on a microwave oven in the door, there's that grid, or it's got those little tiny holes, right?
Mm-hmm.
Do you know what that's called?
No.
It's called a Faraday cage. So basically, the size of the holes are small enough that the microwaves get stuck and they can't get through. So
Mm-hmm.
light can get through because a photon is way smaller than a microwave. Basically, the photons in the visible range. The the height of the waveform is such that the microwaves can't get out of those little tiny holes, right? In fact, those holes are much smaller than you need them to be. They could be much larger, like they could be like a quarter-inch across, but for some reason they don't make them that way, although that would function correctly. Um, so when you talk about things like, basically the amplitude of the waveform is what dictates how big those little holes need to be. So if you were going to design some sort of shield for you know, someone to protect someone, radiologist, basically, in the lab or in the clinic, I suppose I should say. If you wanted to design a shield for them that they could see through, well, you'd have to know about Faraday cages potentially. Maybe you could design something that did that, or you would, know how it functions. Oh, this is because of the amplitude of the waveforms we're trying to block, right? So anyway, I'm getting off topic a little bit, but this kind of concept is relevant. And I had a better example, but somehow I just forgot what it was, and I went off on the microwave example. Oh well, I'm sure it'll come back to me. Anyway, if I remember it, I'll bring it back up again. So this is not specific to anything in biology, but it's the example I have prepared, so I'll go with it. So what this is basically saying is we have a plane. I'm going to do a real broad picture. Plane goes something like that for a while, and then it turns to the left. I should have drawn that differently. Goes that way for a while, and then it turns to the left like that for a while. And the question is, what direction is this resulting thing? So I need to know what is that angle. Okay, so I'm going to redraw this a little more carefully. That's just broadly what we're doing. I'm going to mark out the path and then calculate, okay, what angle is it now from the original airport? So if I make a north-south and east-west line and say that the original airport is here at the center, then I'm told that the plane goes north 35 east. So that's going to be north 35 east. It'd be like that, I guess. Okay, so that's the first leg of the flight. And then the plane turns 90 degrees to the left. So like that, right? Now, I have to be careful because the first part of the trip, going in the wrong direction, is 80 minutes flight time, which at 600 miles per hour, that's a lot. We'll figure that out in a minute, how many miles that is, but that's quite a bit. But then after the turn, it's only 40 minutes. So this side of the triangle is not as long as the first one. So I have to be careful when I draw this. Maybe I've drawn it too long. Maybe the, oops, sorry, hit the wrong button there. Maybe it's like that, and you're now due north. I don't know how far past the due north line I need to go. So I'm going to draw it slightly past it, but I don't know that for sure yet. Okay. So ultimately what I want is I want to know what is this angle right here. It's kind of hard to, I think I can make this smaller. Yeah. Okay. What's this angle right here? That's what I need to calculate. And that's going to, I mean, I chose these numbers not without being very careful about it. So it's because the 40 minutes is half of the 80 minutes, it's not clear if that pink region really should be on the left or the right. Anyway, we'll figure it out as we go. So as I said, this is a right angle. I need to figure out how far is this path and how far is that path. So this first path, and this is 80 minutes of flight time at 600 miles per hour. So I can convert the 80 minutes into hours. So 80 minutes, we'll see like that, equals, well, if I divide by 60, I'll get that in hours. So this is 80 over 60 hours, right? Now, if I say I want to convert that into miles, well, if I have hours and I multiply by miles per hour, right? The effectively, units work like fractions. I will get miles. Maybe this is something that you already know. So if I do 80 over 60 hours and multiply by 600 miles per hour, well, for one thing, I can cancel the hours, and so I'm going to get miles as a result. And also, I can reduce those two zeros, and then this 6 and this 6 can reduce, and that becomes a 10. So then 80 times 10 is 800. So that's going to be 800 miles. Does that make sense?
Yes, sir.
Okay, so I'm going, or the plane rather, is going 800 miles during that time. Can you tell me? So that's this part of the trip, 800 miles. Can you tell me how far the other section is? This one right here.
Yes. Maybe 400.
Yeah. Give me a second. Just log into my email. It occurred to me that someone might be emailing me. Someone in the class might be emailing. Oh, I can't get into the Zoom call. If I don't have my email open, I'm not going to see that. No, no one. Okay, never mind. Okay, so yeah, 400. So I know this is 800. I know that this is 400, right? Now, I would like to know this angle here. Okay, so we'll call that one. This picture's kind of cluttered. I really should have drawn it larger. In fact, I'll just redraw it real quick. It won't take that long. So it turns out I don't need anything below the east-west line. So I'll just do it like this. So let's do it like that. And again, I don't know if I'm ultimately going to have the endpoint be past that due north line or not. I don't know if that's drawn too long, and we'll figure that out as we go. So this is 800. This is 400. And I want to know, again, this is not drawn the best, so I'm going to have to do it like this. I want to know what that angle theta is. And that includes, basically, that goes all the way from this side all the way to this side. It does not stop at that due north line. It kind of looks like it does, but you can see that, or I can fix it so that it does. Okay. Okay. So, can you tell me how I could find out what theta is from that diagram?
You do opposite over hypotenuse. I mean, opposite over adjacent.
Yeah. Now, I could do opposite over hypotenuse, right? If I really wanted to. What
Right.
would I have? Yeah.
You have to do the Pythagorean theorem to
Right. I'd
find.
have to. Yeah, it's an extra step. So I don't want to do extra steps if I can avoid them. So we'll do opposite over adjacent. Exactly. So we'll say tangent theta equals, well, opposite over adjacent. That's 400 over 800, right? Or 1/2. So tangent theta equals 1/2. So theta equals tangent inverse of 1/2. I need a decimal approximation for that. Tangent inverse 0.5. I get 26.565. degrees. Okay, so based on the original question, and maybe you can tell, maybe you can't, and that's okay either way. Can you tell if I've drawn this correctly so that this extends past the due north line?
No.
Okay, so okay, that's cool. I hesitated because I wasn't sure because I asked the question badly because when you say no, I'm left thinking, oh, does he mean he doesn't know or no, it's not incorrect? But okay, sorry about that. So it turns out this is drawn incorrectly. Let me clarify why.
The only reason I say no is because if it's 35 degrees north 35 degrees east,
Yeah.
like the tangent theta should be higher than 35. But since it's lower, it's not drawn right.
Oh, exactly. Yeah. If in fact this is correct, then theta should be more than 35. Exactly. That's precisely right. So this is drawn incorrectly. So let's fix the drawing. So get rid of that. Get rid of that. So it should be more like that.
Right.
Okay, so here's theta, which we've now calculated. So I know that this angle theta is about 26 degrees, roughly 26 and change. Do you see how I can find out what this one is? Because this would be the new bearing. This would be the new deviation from due north.
Okay.
Can you tell me how to get that green region now that we have a number for that pink region?
Couldn't you subtract the 35 from the 26?
Other way around, but yeah, that's basically the right idea. So I'm going to call this one phi. It kind of looks like a loopy 4. Oops. Okay, so phi plus theta. Oops. Not alpha. Phi plus theta equals the original 35 degrees. So now that we have that theta is about 26, that means phi is going to be 35 minus theta degrees, 35 degrees. That's approximately 35 minus 26.565. So that's going to be, I think, what, 8.435? Double check that with the calculator. Yeah, 8.435. Okay, so this 8.435, this is the new deviation from due north. That is the heading out to where they are at the current time after the course correction and after 40 minutes. So that means my result, can you tell me what it is based on that number?
I'm sorry, say that again.
Yeah, so I've calculated the new deviation from due north. Can you tell me how I should write my final answer?
Um, and they're going to east, you said?
Right. Yeah, they're still on the right-hand side. They're still in quadrant one, so that would still be east. Yes. And now they're headed west, but their current position is still to the east.
No, I don't know.
Okay. Well, um, if this is, let's phrase it this way. So when the plane first leaves and they're going north 35 east, right? Well, if they go in a straight path, that's the direction they're at the entire time because they didn't turn, right? But after they turn, now they're going to go this way, right? There was like a big mistake in the flight plan they have to correct. Like it's a big correction. They might even have to stop to refuel or something. So now they are not moving directly towards or away from the original airport. They're moving laterally, right? So their bearing changes over time. At this point in time, their bearing is like north 20 east, and then like north, I don't know, 8 east, and then due north, and then north 10 west, and then north 20 west, right? Excuse me. As they go along, their bearing changes. So that's determined by, say at this point, that's determined by what is this angle right here. That determines how you refer to their new bearing. So in the case of what we've calculated after the 40 minutes, this angle right here is how you refer to the bearing, and this is the number we calculated to be 8.435.
Mm-hmm.
So their current bearing at that time would be north 8.345 degrees east. So this position right here is north 8.435 degrees east, and that would be our final answer.
But I thought you said they were going west.
They are. Their current path is to move in a westerly direction, but that is not what the question says. The question doesn't say what is their heading. It says what is the heading from the original airport.
Okay.
Yeah. So exactly, if the question were different, like if the question is what is their current heading, that'd be totally different, right? And that's the thing. If we wanted to, we could calculate. Like we could say, oh, make a different color here. We could say from this position with their current path, what heading is that? And we'd have to draw a new north, south, east, west line and then redo the calculation, which is a question we could do. That's just not what was asked. So yeah, you have to be careful about what the original question asked, which you've probably noticed in like your previous algebra class that whenever you're doing an application problem, it's very important to make sure you're answering what the question was asking for and not, spend time answering something that's, seems similar, but is actually not what was asked for.
Okay.
So does that question, now that we're basically done, does that more or less make sense?
Yes, sir.
Okay.
I was just
Uh,
taking it as when you were saying going west, I thought we would have to subtract the 8.435 from the 90 and say like east and like subtract that and get that answer and then go from east wherever that is
yeah.
west.
Yeah. So with this kind of problem, you do have to be careful because there's lots of different options as to what you could do. And yet, basically, you have to draw it out. I don't think you really can do these kinds of problems without drawing it. I guess someone can, but I can't. Um, so yeah, but that makes sense now, right?
Yes, sir.
All right, cool.